All right, here is a quick example where we can apply first or second derivative test to tell where f has local maximum or minimum. And then we can also use our theorem to find inflection point of the original function. So suppose this is the graph of f prime from 0 to 6. So we are using interval from 0 to 6. And let's say f prime looks like this. And we want to find where f is increasing and decreasing. F increases on, well, we need to know where f prime is positive from 1 through 5. And then f prime has a negative sign on intervals from 0 to 1 and then from 5 to 6. 0 to 1, union 5 to 6. And then local maximum and minimum. Well, let us use the first test. So first derivative test. Whenever f prime changes sign from negative to positive, original function must be decreasing and then increasing. So our f must have local minimum. And whenever f prime changes sign from positive to negative, our function must be increasing and then decreasing, local maximum. So f has local maximum f of 5, and then f has local minimum f of 1. For the inflection points, we need to know where f double prime change its sign. So we can briefly sketch the graph. When you take derivative of this guy, well, now that f prime is increasing, derivative of this guy must be positive, right? So something positive and then negative, and then positive, and then negative. So that's the behavior of f double prime. So graph of f double prime looks like this: positive, negative, positive, negative. Again, f double prime is positive because f prime is increasing on the interval, and f double prime is negative because f prime is decreasing. And similar for the next interval, f prime is double prime is positive because f prime is increasing. Okay, once you have graph of f double prime, you can tell where it changes its sign. So f double prime changes the sign from positive to negative at this point 2, then positive to negative at 4. So we have inflection points, and then f double prime changed its sign from positive to negative, from positive to negative, and then negative to positive at 3. So we have 3 inflection points. So combining, we have inflection points at x equals 2, 3, 4. Well, you can describe the behavior of the function in detail. When x equals 2, it changes sign from positive to negative, concave upward to downward. So upward to downward, like this. And then at 3, it changes concavity from negative to positive. So concave downward, and then upward, like this, and then downward.